Okay, so as we went over yesterday, we're talking about inorganic nomenclature. So non-organic compounds, which are things that do not have a carbon in them. And specifically with this note that we're talking about ionically bonded compounds, which is a metal. So things on the left side of our periodic table, bonding with a non-metal, which is things on the right side of our periodic table. And you all have been making elements for the wall, and hopefully you've identified whether the element that you've created is a metal or a non-metal. And then the process by which those bond is electron movement from a metal to a non-metal, creating a positive charge on the metal, so a cation, a negative charge on the non-metal, making it an anion, and then our opposite charges attract and create a really strong bond. Creating a strong bond, an ionic bond, that holds them together as a compound. Okay, and then we were just getting into how to actually create the formula when we're given different compounds. So, for example, we were given calcium and chlorine. We figured out using our periodic table that calcium is in this row, which has positive 2 charges when it's an ion. So it gives away 2 electrons. So we wrote down the ion of calcium, which is Ca2+. And then we figured out that chlorine is over here. It's a nonmetal that's in this row that accepts 1 electron or can accept 1 electron and creates a -1 anion. So in this example, I drew out the electron movement to show that calcium is giving up 2 electrons, creating a 2+ charge. Chlorine can accept 1, so we needed to have 2 chlorines in order to balance out that calcium, giving us this formula. And I showed you all the shortcut method, which is crisscross. Has anybody heard this called something else, the crisscrossing? No? I think that some teachers might call it like the drop-in swap as well. I've heard that. And did you all use this in your Science 10, this method? I'm getting some thumbs up and a few nods. All right. So we're just going to do a couple more examples here. And hopefully you went through the worksheet and have done a few of these, so these will hopefully make sense to us. Magnesium oxide is the first one we're going to do. So can anybody tell me what the symbol for magnesium is? Mg, beautiful. Okay, and how many electrons does magnesium generally want to get rid of? 2. So it likes to form a 2+ cation. And then oxygen. So magnesium oxide means magnesium and oxygen. Oxygen is over here. Oh, and how many electrons does oxygen like to receive? 2. Yeah. So it's in that 2- column. Yes, exactly. So it does cancel each other out. If we've got one thing that likes to give away 2 electrons, so I'll just do the Lewis dot diagram for this. Magnesium has 2 electrons to give away. I'm just going to draw oxygen's electrons as X's. And oxygen can accept 2 electrons. Magnesium is happily getting rid of those 2 and becoming positively charged. Oxygen is becoming negatively charged. And yes, we only need 1 of each in order to create a neutral compound. So MgO. Now here's the thing. If you use that shortcut, I talked about this a bit yesterday briefly. If you use that crisscross shortcut for this, what you're going to end up having is Mg2O2. But we do want to put this in the simplest terms. So if crisscross, you'll end up with this. You've got to simplify to just MgO. Does that make sense? So next one up is barium carbide. And do you all remember when you're naming things, changing the endings to IDE for the second one? Yeah? Okay, good. So barium is Ba. And what is the charge on barium after it ditches its electrons on the valence shell? Yep, awesome, 2+. Okay, and carbide, carbon. Okay, carbon is a bit of a weird one. So we didn't actually write down a charge on carbon because it doesn't normally form an ion. You know what? I'm actually going to change this. I don't want to do this with carbon because I'm not going to give you guys a question like this because you wouldn't know what this is. So let's instead do nitride. So just cross that out. Nitride. Okay. So nitrogen, it's in this row here. So it has got space for 3 more electrons on its valence shell, its outermost shell. So its ion is a 3- anion. So then what we're going to do is go, I'm just going to do the crisscross method for this one. Ba 2+ and N 3-. I'm swapping those charges. Ba 3 and 2. Okay, a really important thing about this is when we're writing the numbers up top as superscripts, so that's a superscript, that indicates charge. When we've got a number on the bottom like this, a subscript, that tells us how many. So that's just a really important distinction to make. The superscript is charged, so it's going to have either a positive or a negative associated with it. It's telling us how many extra electrons does that have, or how many fewer electrons does that have than protons. The subscript does not have a charge associated with it. It's just telling us how many of that thing there are. So this compound, if I were to draw it out, would be like 3 bariums attached to 2 nitrogens. So that's what that's telling us, is what this compound actually looks like. There's 3 bariums, 2 nitrogens in that actual chemical. Does all of this stuff make sense? Does anybody have questions or need clarification around the crisscrossing or what those numbers mean, or how to find the charges? Okay. Okay, so let's move on to polyatomic ions. Does anybody remember polyatomics? Nobody remembers polyatomics? Okay, that's right. Polyatomics are actually charged compounds. So instead of just an ion that has a charge, like lithium having a +1 charge, it's something that's already multiple elements together, but it has a charge overall. So we're going to just talk about what happens with sodium chloride here, NaCl, when that breaks apart into the ions. When we actually break that down and we see like what's in there, every atom inside of that forms a separate ion. So for this example, it's Na plus and Cl minus. So individual atoms are separated and have a charge. Okay, now some atoms, and this should actually say compounds, but some compounds don't come apart into separate ions, but groups of atoms. and those are called polyatomic ions. So the example given here is H2SO4. That is sulfuric acid. Sulfuric acid actually breaks apart into H+, so that's one atom with a charge, but it also breaks into HSO4-. So that's a group of atoms that has a charge, or a polyatomic ion. So polyatomic ions, they can look a little bit confusing for people when they're in a formula. Like H2SO4, or sometimes we would see like Na2CO3, and I might ask you to name that or something, and people start kind of freaking out, and they're like, sodium carbon-oxide. But whenever you see a bunch of different symbols here, a bunch of different atoms, in general, that means that you've got a polyatomic involved. And when it splits, you're going to see sodium ions and carbonate ions. So if you see a whole bunch of atoms or elements kind of paired together in a compound, generally that means you've got a polyatomic, and they're actually, I think, even easier to name than the ionic compounds, because you don't have to do anything with the endings to them. So here's some compounds, some examples of polyatomic ions. You should know these. I'm gonna not put must. We're gonna get rid of must, but you are gonna become familiar with these ones. We're gonna use these ones a lot, and you should at least have an idea that when you see CO3 2-, that's carbonate, and when you see NO3-, that's nitrate. So I'm not going to make you memorize these, but you are going to see these frequently, and having them memorized will help you work through things faster. Okay. So let's do some examples. Okay. So I just did this on the last page. Chemical formula for sodium carbonate. So when we see a name like this, if this ended with IDE, it would be a simple ionic compound. But because there's an 8, so as soon as there's an 8 or an ite involved, it generally means that you're working with a polyatomic. So what you're going to do is, okay, I've got sodium, Na, and that's got a charge of 1 positive. And then carbonate, okay, I'm going to look on my polyatomics here, and I'm going to see that carbonate is CO3 with a 2- charge. So that whole ion, this entire thing, has got a charge of 2- when it's an ion. So it can accept 2 extra electrons into it. You can still do the crisscross method here. So generally what I like to do is I do put my polyatomic just in little brackets when I'm kind of setting this up. So then I'm going to crisscross. And my sodium is getting a 2. My carbonate, there's only going to be one of them. So I am just going to take it out of the brackets and just put CO3. So that's sodium carbonate. But now we're going to look at one where our first thing, our cation, isn't just a 1 charge. It's got a positive 2 charge. So I've got calcium phosphate. What is the charge on calcium when it gets rid of electrons? Yep, 2+. Great. Okay, and then can anybody tell me what phosphate is? Yeah, awesome. And it's PO4 3-. Okay, so this is why I like to do this bracket thing. So I'm going to go Ca has a 2+, And then I'm just going to throw PO4 here in brackets. 3 minus. Okay, so what this means, when I do my crisscrossing, I'm going to have Ca3. And technically, sorry, we're supposed to use these things, parentheses, not brackets, but anyway, PO4, 2. So the 2 needs to go on the outside here. This Ca3PO4, 2 is not correct. You need to include those brackets when you've got multiples, because what this is telling you, this 2 is saying I've got 2 phosphates. So I've got 3 calciums, I've got 2 phosphates. So if I'm drawing this out, I've got 1, 2, 3 calciums, and then I've got 2 of this whole PO4 molecule. So that means I've got 2 phosphoruses and actually 8 oxygens. So it's really important to make sure that we're including brackets when we're making formulas for our polyatomics. Yeah. Just leave it like that. Yeah. Generally with chemistry, we like to keep things kind of simplified. There are exceptions to that where we will write out like multiple, like we'll have like 2 oxygens and they're like written out separately, but for the most part, we like to keep it simplified and kind of tighter. Okay, can you guys all try calcium nitrate and ammonium dichromate on your own? And I'm just going to give you a hint. This is a polyatomic cation. Okay, so give those a go. Ammonium is on your polyatomic sheet. Okay, I'm going to show you the answer in just 1 minute. Something really exciting is happening across the hall. That sounds like they're popping the loop or something. Okay, let's check our answers and see if we all got these right. Okay, so did everybody get this? Yeah? Yay! Okay. Good. Okay, and does this process make sense to you all? Yeah, these ones are pretty straightforward. Hey, you just have to find the things and cross the charges. Okay, next up. Now, this one is honestly, this is the thing that I see confuse people more than any other thing in naming. Is multivalent ions. Do y'all remember hearing multivalent ions before? Yeah? Okay. So here is the I'm just going to show you guys like what the problem with these are, and I'll write this on here. Is I have a blank piece of paper. Just going back to this. Okay. So say I give you, I'm like, okay, I've got copper chloride. Let's look at our periodic table for copper chloride. What's the charge on chlorine? Like if we're trying to write a formula, what's the charge on chlorine? 1 minus. Good. Okay, what about copper? We don't know its charge because it's one of those ones that's in the transition metals. So it's not in our first 3 rows and is not silver, zinc, or cadmium. So we don't know what the charge on copper is. If we're just given the name copper chloride, it could be +1, +2, +3. We don't know. And copper 2 chloride, so CuCl2, has very different properties from copper chloride, that's CuCl, with a 1+ charge. So it's really important that in the name, we include the charge that's on copper or on any of the metals that are not in those first 3 rows that we can identify, so that a person who's getting the formula from that knows which copper ion they're working with. So what that's called is a multivalent ion, and that's metals that have more than one possible charge. So what we actually do in order to indicate which version of a cation we have is we use a Roman numeral after its name. And that indicates the charge on the metal in that specific compound. So, for example, here I've got copper 2 sulfate. So what this tells me, the copper 2, is that I have Cu2+. And then can anybody tell me what sulfate is? SO4 2-. Good. No, this is positive. So any metals always form positive ions, cations. So anything that is on the left side of our staircase here, all of the metals form cations, positive ions, and our non-metals form anions, negative ions. So these guys are electron acceptors. These guys are electron donors. So yeah, we don't need to include a charge in that name either. So copper 2+ and SO4 2-. Do we need to do that drop-in or the crisscross method for this? Yeah, exactly. It's 2+, 2-. We know that those cancel each other out. We just need a 1-to-1 ratio. So this is CuSO4. Now, if somebody's working backwards from this, they're going to know there's a 1-to-1 ratio of these. They're going to be able to look up the charge for sulfate and see that it's 2- and go, oh, okay, that copper has to be 2+. So it's really important that when we're working backwards from our formulas, we're including those ions in our names. Yep. around the polyatomics. Yeah. So if there was going to be a number here, so say this wasn't a 1-to-1 ratio, if this was like we needed 2 sulfates, we would need to put brackets around here for a 2. I think the next one will need to do that, so I'll show you the difference. Okay, chemical formula for iron 3 carbonate. What does iron 3 mean? Fe with a charge of what? 3 plus or minus? Good, because it's a metal. Can anybody tell me what carbonate is? Good, CO3 2 minus. Okay, so here's an example of a time that we are going to use brackets in our formula. So I'm going to go like this. I'm going to do our actual crisscross setup. Throw in this guy in brackets. So now I'm crossing these over. And I'm going to end up with Fe2 and then CO3, and there's 3 of those. So it's important that this is in brackets in this case because there's 3 carbonates. So what this tells me is there's 2 irons and 3 carbonates in this molecule. So that's why those brackets are important, is just so that we've got this number on the outside and it doesn't look like there's, if we were to just write it like this, it would look like there were 33 oxygens. So no, don't do that. Does that make sense for why we need the brackets? Okay, can everybody try the silver 1 phosphate on their own? And I'll put the answer down here and then show you in a minute. Okay, I'm going to pop this up here. Check that you, or maybe I should hide this for a second more. Okay, check that you got the right answer. Did anybody not get this? Okay, cool. Okay, any questions about writing out formulas, when to include brackets, when to include Roman numerals? I'll make a flow chart on the board afterwards as well, that kind of runs us through like when we need to use those things. But first we're going to talk about naming. So this is just the opposite of what we've been doing so far, going from the compound's formula to its name. So we always write the cation first and the anion second. And then we change the ending of the anion to IDE in simple ionic compounds, which means when there's just 2 elements, 1 cation and 1 anion. As you all saw, when we're working with polyatomics, we do not change the endings. Okay, so let's pop over to the next page here. Na2O. So what we're going to do here is go sodium. Okay, now you guys, for sodium, Do I need to specify the charge of it with Roman numerals? No, because we know that it always has a 1 plus charge, so I don't need to worry about that. And then oxygen, I'm changing the ending, so it's oxide. Got to remember to change that ending. So that's oxide. Sodium oxide. Okay, next one is calcium and OH. So calcium, do I need to specify the charge on calcium? No, it's in the second row. Yeah, Amber? Great question. So if I go to reverse this, so let's go like this. Say I were given the name sodium oxide, I could go Na, and we know that sodium has a 1 plus charge and that oxygen has a 2 minus charge because we're given that information on our periodic table from just which row it's in, or which column rather. With ionic compounds, you can just drop these and change them. And based on the charges, you're going to be able to get your end result. With covalent compounds, which are when our metal or our non-metals bonds to each other, we're not given that charge information. So we can't just figure out based on charges how many you need to make a neutral compound. So in molecular or covalently bonded compounds, we do use those prefixes, the di, tri, mono. Do you all remember doing those? Yeah. So for ionic compounds, no, you don't need to use those. Yeah, but really good question. Okay, so calcium, do I need to put Roman numerals after this, or do we know the charge on it? Yeah, it's in the second column, so we don't need to do that. And then can anybody tell me what OH is? Yep, hydroxide, awesome. Okay, this is a polyatomic. I do not need to change the ending of it, although the ending is already IDE. Okay, next one. This is on our polyatomic page. It is pretty much the only positively charged polyatomic that we'll work with. It is ammonia. And then SO4, sulfate, right? Yep, sulfate. Ammonium sulfate. Sulfate, you guys can spell this with a PH or an F. It does not make a difference. It's just an American British thing, like color with a U or with just an O. So it's okay if you put this with an F or with a PH. Either way is totally acceptable. Okay, any questions on reversing this and going from compounds to names? Yeah. So Roman numerals are, let's actually do a Roman numeral example. So I'm going to just throw another example down on the side here. Okay, so let's do FeCl2. Okay, FeCl2. Okay, so I'm going to write the name of my cation first. So Fe is iron. Okay, if we look on our periodic table, do I know the charge of iron? No. So we need to figure out what the charge of iron is based on this compound, based on this formula, and we need to put it in Roman numerals. So I'm just going to leave a space for that. Cl, that's chlorine, right? So I'm just going to go chlor, change the ending to IDE, chloride. Okay, now we're going to figure out which iron this is. Is this iron with a charge of 1? Is this iron with a charge of 2? So the way that I like to do this is either you could just go, okay, chlorine has got a charge of -1, and there's 2 of them. That means that iron has got to have a 2 plus charge. Or you can do the reverse crisscross. where you go FeCl2, and you're just doing this, and you end up with Fe2 plus Cl1 minus. And then you're like, okay, it's my iron 2 cation. The one dangerous thing about doing this is if you had a 1-to-1 ratio of something that had a -2 charge, you would just have to take note. Like if this was oxygen and you ended up with a 1 minus, you would have to be like, oh, wait a minute, oxygen has a 2 minus. That means I need to double these both. Does that make sense? Okay. So you can just work backwards to figure out these names. All right. So, oh yeah, and we're gonna go over that in more detail. So for the multivalent metals, so multivalent just means can form more than one ion, 2 or more ions. That's just the name for that, multivalent. You have to specify the charge with a Roman numeral. Okay, but yeah, again, as I kind of went over here, you have to first predict what the charge is from the formula using the anion's charge. So you guys are always going to know the charge on anions, on our negative ones. So that's what you're using to predict the positive charge on our cations. Okay, so FeCl2, oh, we just did that one. Okay, so you just throw an arrow up here. We did that one already as an example. I got a little bit ahead of us in the notes. Okay, but let's do Fe2O3. So if I look at this, what I have got is 2 irons with, I don't know what the charge is right now. I've got 2 irons though. And I've got 3 oxygens, and oxygens have a charge of what? 2 minus. Awesome. Okay. So that means I have got, this is kind of another way to do this. I've got how many negative charges in total? 6 negative charges. Okay, good. Now I need to have 6 positive charges in order to balance that out. So if I've got 2 irons, they have to have the same charge. What does the charge on each one have to be? Yep. So therefore, Fe3 plus. Okay. And then you could also do this with that reverse crisscross thing that I showed you as well. Yeah, that would be another way to do this. Okay, so we're going to name this iron. What am I putting in my brackets? Awesome, 3 in Roman numerals. And then oxide. That's my name. Well, that's the compound's name. Honestly, science is just, this is like another language. A lot of science is just learning a new language, especially in chemistry. The language is IUPAC. Alrighty. So it is 9:48. I am just gonna really quickly, so I'm gonna just show you guys, like, this is what you need to do for homework from this is page 71, 72, and then the rest of that worksheet that you all got the other day. And then I just want to go through a couple examples about naming molecular compounds. So this is what Amber was asking about with the prefixes. Oh, sorry. Did you have questions about this? Is anybody else, are you guys confused by this at all? Do you want me to run through it in more detail, or are we? Oh yeah, totally. Okay. Let me let me go through this in a little more detail. Okay, so yeah, let's just do a couple more examples. And hopefully that will help. Okay, so I'm gonna go, so you guys can write this on a separate piece of paper if you want, or you can just watch and listen. Either way is fine. I'm gonna go MN 04. Okay, MN04. All right, so the way that I'm just gonna write this out is I'm gonna write out what I actually have in this formula. So I've got 1 Mn, which is manganese. So what I have, what is in the compound is 1 manganese. And how many oxygens? 4 oxygens. Okay. Now, do we know the charge on manganese right now? Like just immediately, do we know it? No, we don't. So I'm just going to throw a question mark here. Do we know the charge on oxygen? What is it? 2 minus. Yes, excellent. Okay, so because I've got 4 of those oxygens, and I'm just going to draw this out because that often will help me. I have got 1 Mn, and then I've got 1, 2, 3, 4 oxygens, and all of those oxygens have a 2 minus charge. So in total, how many negative charges do I have? 8. Yeah. So 8 negative charges. In order to balance that out, whoa, I made this like a really intense compound. I didn't mean to do this. I don't think this exists, but we're going to go with it. What does my manganese have to have a charge of if I've got 1 of these and I need to balance that out? Yeah, so this has to be 8 minus in order for that to work. Sorry, yes, A plus, my bad. A plus, thank you. Okay, so we're just trying to make the total equal 0. So then my name would be manganese 8, which is VII, oxide. Again, I don't think that compound exists, but that's the idea behind it. Do you guys want one more example of these? Okay, so how you would go from here to here. Yep, okay. So let's do another one of those. Okay, so let's say I am given nickel, 2 fluoride. Okay, so I'm told I've got nickel 2 fluoride, and I need to figure out what is the formula for this. So nickel is Ni, and what this 2 is telling me is that the nickel has a 2 plus charge. And then if I look at fluoride on my periodic table, what's the charge on fluoride? Yep. Okay, so it's much easier going from name to formula. This is just like how we would do with simple compounds, simple ionic compounds. We just do the crisscross, and I end up with NiF2. Does that make sense? Okay. Is going from name to compound okay for people? This one? Okay, so if I were just given this name and nothing else, I would go, okay, I've got manganese, Mn. There's an 8 in brackets here. So I would go 8 plus. And then I would go oxide is oxygen. And I've got 2 minus, because oxygen is always 2 minus. Okay, this one actually, you guys, is a little bit trickier. I'm going to drop and swap these, and I'm going to end up with Mn2O8. Okay, but remember how in that one example I said we have to simplify things? So what are these both divisible by? 2. So I'm just going to go Mn. For every 1, there's 4. So I'm just simplifying. Yeah. Okay. Does anybody want another example, or are we feeling okay with that? Okay. So those are ionic compounds. You know what? I think I'm going to save covalence for another day so that we can take some time to work on our elements or our or these questions, and we'll do covalence tomorrow. Okay, so what you guys are doing until 10:05, so you've got about 15 minutes, is either these things or your element tile. So you can work on either of those. At 5 after 10, we're going to do a 15-minute break, and then Ms. Hartling is going to give a lesson after that. So I'm just going to hit